All right, so should probably make sure we understand what secant lines are. But when we have a circle, last week we talked about chords, and a chord was a line that had its endpoints on the circle. Right, that made a chord. A secant line is just like a chord, except it goes forever in both directions. Okay, so it still intersects a circle in two places, right? But then it goes forever once it leaves the circle in those directions. Okay, so what we're going to be talking about are two secant lines, right? And the angles that are made within those secant lines and how they work with relation to the circle. So to start off, we're going to be showing how two secant lines intersect a circle. They can intersect at one of three places. They can be on the circle. And what's nice about these types of angles is that these angles are the angle that is inside the circle. That is an inscribed angle. And we know about inscribed angles and how they relate to circles and the arcs. We know this inscribed angle is half the measure of the arc. So that definitely helps us out. We know some relationships with these types of angles in circles. It could intersect inside the circle. These are a little bit tougher, but the nice thing is there are some equations and formulas you can use when it comes to these angles. There's also the unique situation where this intersection could be on the center of the circle, which would make those central angles. Which again, central angles are very nice because they're equivalent to the arc measures that they make on the circle. But the last place would be outside the circle. In this case, we have our two secant lines, and they would both go through the circle, but the intersection of those lines is outside the circle. Let's take a look at these different situations. All right, if two secant lines intersect on the circle, the vertex of the angle formed on the circle making it is an inscribed angle, and the measure of the intercepted arc will be twice the measure of the angle. So, long story short, we've done these types of angles before. We know if that measure is x degrees, then that arc there is going to be 2x degrees. We know that this measure is half of that measure. So nothing's really changed with that. It's inscribed angles are things we've worked with before. So we're pretty good on that. If we went the other direction and said this is x, then this angle would be 1/2 x. All right, here's where they start to look a little bit more confusing. And as with everything, we will have a cheat sheet that will have a lot of these different circle theorems in one place for you guys. But I recommend that you write these things down as you're working today so that when you're doing your assignment, they're easier to use. If two secant lines intersect inside the circle, the measure of the angle is 1/2 the sum of its intercepted arc and the intercepted arc of its vertical angle. All right, so here's how this one works. We know that this angle right here, okay, angle NIP, actually, they used MIQ, but we'll use MIQ, that way we're being consistent here. MIQ, we know this angle is going to equal 1/2 times this arc plus this arc. Okay. Now, another way to say that is this angle equals the average of these two arcs.
What about MIQ equals MQ?
The only way MIQ would equal MQ is if this intersection point was at the center.
Oh, that's what we talked about before.
Yeah, so if you have the intersection point at the center, then those become central angles, which are gonna be equal. The equation would still work because you'd be finding the average, if this were a center, you'd be finding the average of these two central angles, which are gonna be equal. And the average of equal angles is the exact same thing. But in this case, I know that MI cubed is gonna be equivalent to NIP because these are vertical angles. But each of those angles are gonna be equal to the average of these two arcs. You have to add them together and divide by 2, or do 1/2 times the sum of those two arcs. This bottom equation is just looking at these bigger angles up here. So we got NRM, so let's use this one. Angle NIM, NIM is this angle, which is equal to this angle. You have to take the sum of the top and the bottom, and then find the average of that. Once you do it a couple times, it's pretty straightforward. I think the hardest part of this is just making sure you're using the right equation. But the actual math that's involved isn't terribly difficult. So here's an example where we're trying to find the measure of angle 1. I want to find this angle right here. So I have to take, I always think of it as average. And when I think of average, I think of adding together and dividing by 2. So angle 1 is going to equal the sum of these two arcs divided by 2. 45 plus 35 is 80. And 80 divided by 2 is 40. So angle 1 is 40 degrees. Okay. And what's nice is this works no matter where these angles, these two secant lines intersect within the circle, as long as you know the two arc degree measures. If you find the average of those, you will get your angle measure. Okay. Right, here's another one where we're given the angle measure, but now we need to find one of the arc degrees. So I'm going to use the same equation. But in this case, I know the interior angle is 145. And I know if I add my two arcs, x plus 150, and divide by 2, it should equal 145. Now, you could probably do this in your head. You can figure out, all right, what angle does this need to be so that the average between that and 150 is 145? Yeah, it's going to be 140. But let's say it's not that easy and it's not something you could do in your head. You could set up an equation like this where you've got x plus 150 over 2 equals 145. So the average of the arcs equals 145. To multiply both sides by 2. And then subtract 150 from both sides. We get 140. Okay. All right, outside. A little bit different. The equation's a little bit different. We're not finding the average now. All right, we're taking the difference of our two arc measures and we're dividing by 2, or multiplying times 1/2. Same thing, multiplying times 1/2 divided by 2, same thing. But if the secant or tangent lines intersect outside the circle, the measure of the angle is 1/2 the difference of its intersected arcs. Now, when it's outside the circle, there's always going to be one arc that's bigger than the other. Okay. So you're going to find the difference. You're going to take the bigger arc and subtract the smaller arc measured from it. Okay. And again, I could rewrite this like that as well. And to be honest, that's usually the way I would solve it in a calculator. I just subtract and then divide by 2 rather than multiplying times 1. But you'll get the same answer because it's the same operation. Let's use a couple examples with this because I'll wait a second. I'll put it down still. All right. So here we're going to take our, so if we want to find angle 1, take our bigger arc, 100, minus the smaller arc, 40, and divide by 2. 100 minus 40 is 60. Gives us 30 degrees. And you just got to be careful with this as far as how this could easily still be, it's not guaranteed that this angle is going to be smaller than this one. It just depends on how it's, where this intersection point is. If this point was closer to 40, right? You could still have a 40-degree arc here, but this, as you get closer, would make the secant lines wider. So now your bigger arc would have 4 degrees. So you easily could get an angle that's somewhere in between the two. It's not always going to be small. Here's one similar to what we did before, where we've got a degree measure we're missing from an arc. My recommendation is set up the equation. We know that our angle measure is supposed to equal the difference between these. So the bigger minus the smaller divided by 2.
Mr. Gray,
Yes, sir.
I'm going to South back.
Where are you going?
South. I want something.
Okay. Make sure you sign out.
I was happy.
What's up?
It's not a rickroll.
Yeah, nobody's rickrolled today. I saved it for later in case I want to rickroll you guys later on. All right. So multiply times 2. Oh, you don't need that line anymore. There's a couple different ways that we could do this. We could add x to both sides. That's subtract 40. I'm going to subtract 90 from both sides, and I get negative 50 equals negative x, which means x is equal to 50. Once you have 2 negatives, you can multiply or divide both sides by -1 to make them positive. So x equals 50. It's weird looking equal sign. All right, this is the situation. You use the same formulas if one or both of your angles is, or one of your lines, your secant lines, is a tangent. Okay, so you still use the same formulas. There's still 2 arcs that are made here. There's the minor arc DC and the major arc, called DBC. Okay, but there's still 2 arcs. Now, I like this problem because it forces you to do a little bit of extra math here. We know that the difference between the major and the minor arc in this case, when we divide by 2, is going to be 50. Well, let's set up that equation. The big arc is this. How can I represent the big arc numerically or as an expression? I know that this one equals x. What does this arc? What can we say that arc equals? we could give it another variable, but it's hard to, we can't really solve for one of the variables. It'll always be in terms of the other one. But what's a numeric way we could represent this? I know there's no numbers written here, but think about a circle. How many degrees is a circle? Mhm. So how many degrees would this one be? No, not minus 50, minus x. We know that if this is x, then this arc would be 360 minus x. Same thing if this, let's say that this x was like, let's say it was 50. Well, we know the other major arc would be 360 minus 50, so it'd be 310 degrees. We don't know what the actual value of this is yet, but we do know that it is 360 minus x. So that's the big arc minus the small arc, which is another x, divided by 2. We can solve this equation. 360 minus x minus another x divided by 2 is going to equal 50. Well, let's start working this out. Multiply both sides by 2. I'm also going to do a little combining like terms here. 360 minus x minus x. Well, that's subtracting 2 x's. I'm going to go ahead and subtract 360 from both sides. And lastly, I'm going to divide both sides by -2. We get x equals 130. So we know that the measure of this arc is 130. And if we wanted to find the major arc, it'd be 360 minus 130, which this arc would be then 230. Okay. Don't be surprised if you see another problem similar to this. Okay. To say this is one where sometimes you may be given the major arc as x, sometimes the minor arc as x, but you can still solve the problem in a similar fashion. Okay. Here's one where they give us our major arc as x. So we got our 76 equals the major arc x minus the minor arc, which would be 360 minus x divided by 2. All right, now this one, and I should have, when we subtract this, we probably should put that in parentheses. The reason being because we're subtracting this whole thing from x, whereas before we had, let me go back actually and show you. If I would have put this in parentheses, 360 minus x, when I get rid of the parentheses, I'm just multiplying times 1, so that it would go away. The difference between that and the next problem is that when I'm getting rid of the parentheses here, I'm multiplying times a -1. So when I rewrite this, it's going to be 76 equals x minus 360 plus x. So combining like terms gives me 2x minus 360 over 2 equals 76. So I multiply both sides by 2. I get 152 equals 2x minus 360. If I add 360 to both sides, I get 512. If I divide both sides by 2, x equals 256. So there's, that arc's 256. Again, if I want to figure out the minor arc, I do 360 minus 256. And I believe I get 104. Okay. All right. That's it for our notes today. Go ahead and get that assignment posted so you guys can go ahead and get started on it.